Okay, now we're entering a new chapter, and this is chapter 4. We're going to take a look at exponential functions. We'll look at exponential functions, the graphs of exponential functions, and compound interest. We're going to be studying a new class of functions called exponential functions, and how you will know those would be you're going to have a base, and that base is going to be a real number, and then your exponent is going to have your variable. So this is an exponential function with base 2. Now they point out how quickly exponential functions rise. Here we have 2 to the 30th power, which is a really big number, 1,073,741,824. Compare that with 30 squared, which is just 900. So you can see how quickly exponential functions will rise. And you'll hear exponential functions used a lot in terms of rate of growth and decay. When we've been looking at viruses are exponential functions. And we have to define first what we mean by this expression, a to the x, when x is any real number. So we're going to define a to the x when a is bigger than 0, so it's positive, and x is a rational number. So what this means is that we have 5 to the square root of 3, or 2 pi. Those are irrational numbers. So we're not looking at defining exponential functions with irrational powers. Irrational powers such as the square root of 3 or pi. When the x is irrational, though, we can't approximate it by using a rational number, and that's usually how that's handled. So it's not that exponentials do not exist with irrational numbers. They're normally handled by giving them a close approximation to a rational number. So in other words, they're showing you here that this square root of 3 is 1.73205. We might just use 1.7 to approximate what a to the square root of 3 would be. Here we have 5 to the square root of 3. Again, we're going to just take that square root of 3 and we're going to approximate it. Here they're using 1.732. The laws of exponents are still true when you're dealing with real numbers and the exponentials. Again, this is f of x equals a to the x, where a is greater than 0 and x is your variable. Now, they say a does not equal 1 because 1 to any power is 1, so we really don't need to include that. We're going to have a number that's bigger than 0, but we're not going to use 1 because 1 to any power is 1. Here's 3 different bases, so we could have 2 to the x, 3 to the x, 10 to the x. And let's take a look at evaluating some of these. If I have f of x equaling 3 to the x, and I'm going to plug in 2, I would have 3 squared. Or if I plug in negative 2/3, or if I plug in pi, or if I plug in square root of 2. Here are your different values. Now, looking at the graphs of exponential functions, you might have seen in some of the parent functions, you'll see exponential functions. We have not used it yet, but we will. And here they're asking you to draw 3 to the x as f of x and 1/3 to the x as your g of x. Pay close attention here. You will see that if the number is bigger than 0 but less than 1 as a base, so again, the base here, the base is going to be greater than 0 but smaller than 1, in other words, a fraction, you will have the line going this way. If your base is greater than 1, so bigger than 1, then you will have a graph as this red graph going this direction. And there's a table of values to support that. They want you to notice that if you brought that 3 upstairs and that would make the exponent a negative, because remember it's directional, then your f of negative x will be reflecting in the y-axis. So it reflects the y-axis just like the transformations that we looked at before. And that's why the graph will be different for the fractional between 0 and 1 and the number that is greater than 1. So this right here is a great graph to know, at least understand. You will see here that I have y equals 2 to the x on this side. And then if I take that about the y-axis, I get my 1/2 to the x. Now, remember, we just pointed out that this also means y equals 2 to the negative x, which causes that reflection about the y-axis. I want you to notice that the larger the number, the steeper the line. So the larger the number, here I have 3, here I have 5, here I have 10. Notice how much more steep they become, the larger the base. Likewise, if I brought this up and made this a negative exponent, this would be 3 to the negative x, 5 to the negative x, 10 to the negative x. Again, about the y-axis, it will be steeper. All of these graphs pass through the point 0, 1 because a to the 0 is going to be equal to 1. So there are two kinds of functions. You're going to have the function that is between 0 and 1. These are your small fractions. And then greater than 1. So again, just a reiteration of this graph. The x-axis is a horizontal asymptote, and that means it will never come down past that unless after you do this part of the graph, then you cause a reflection to the whole function. If you do, then it'll flip it and it'll go underneath the x-axis. Or if you drop it down afterwards. So all of these have this are affected by the same transformations that we looked at before. Again, what we said, this is just for your a is greater than 1. Over here is if it is a fraction between 0 and 1. Now they're asking you to find the exponential function whose graph is given. So we have to think about here, if this were my x value, if that were my x value, what would I square x by to get, or what would I square x to get 25? Well, hopefully you thought of 5. So this would be y equals 5 to the x. And when my x value is 2, I will get 25. Over here, this would be y equals 2 to the negative x. And then I would get my 1/8. So since I have f of x equals a squared, which is equal to 25, we see that the base is a equals 5. So 5 to the x. And as we said before, if we have f of 3 equals a to the third, and we know that's equal to 1/8, then we're going to have 1/2. Now, I put 2 to the negative x, and remember that's because 2 to the negative x is the same as 1 over 2 to the x. So if I have 2 to the negative 1, that's going to be 1/2. All right, now we have some graphs with some different rectangles. I'm going to kind of go quickly through these graphs. This is just, they want you to zoom in and take a look at the activity from different windows. Here you can see when you have a really large window, you can see that difference in steepness. Now we're going to take a quick look at compound interest. Compound interest is one of those areas where exponential functions are often used. The p-value is what your principal value is. And then you have an interest rate, which is I, or the period of time. Now, this I is different than the imaginary number I. The reason that we use I in this setting is because it stands for interest. And notice it's not italicized like the complex I is. So it's completely different. So here is your formula for calculating your compound interest. P is your principal, R is your rate per year, N's number of interest, number of times interest is compounded, and then the number of years. So here we have a sum of $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. So you're going to plug in these values. Annually means once, semi-annually means twice, quarterly is 4 times a year, monthly would be 12 times a year, and daily would be every day, which is 365 times a year. If an investment earns compound interest, then the annual percentage yield, APY, is the simple interest rate that yields the same amount at the end of 1 year. Finding the annual percentage yield for an investment that earns an interest rate of 6% a year compounded daily. After 1 year, a principal P will grow to the amount of, now the P value is your principal, so we're going to take that principal times 1.06183. A simple formula for interest then would be A equals P times the quantity 1 plus your R, which is your rate. So the annual yield is 6.183%.